So we're going to start the second session of the time delta or power factor testing seminars on a series of WiseGrid webinars here. Yeah, okay, good. There are the main presenter here is Hossein Adashi. So he's and with him, I'm Ali Naderian. Will be presenting this webinar today for you. WiseGrid have been, one of the contributors to the technology, this technology worldwide, and we're hoping through these sessions we not only we work on obviously the business aspect, but the technical part of it, and try to basically spread the word, get the knowledge out, and also get feedbacks from you guys. So let's go to the next slide. Table of contents here. I think this is where you go, Hossein, on to present it for us. And by the way, at the end of the meetings, like as you see here, there's question answers that we can go through. Feel free to keep them until the end.
Thank you, Dr. Ali. Hello, everybody. Good morning and good afternoon. Today, we are going to talk about time delta measurement at power transformer and high voltage bushings. Here, you see table of contents, why we measure capacitance and dissipation factor. First step in power transformer, CNDF testing, winding diagrams for different types of power transformers. I mean, 2 or 3 winding, shunt reactors, and so on. Interpreting power transformer test results, also some interesting case studies regarding power transformer, time delta or dissipation factor testing. I sometimes use time delta or dissipation factor or power factor. They are same words. So, and then we will start with construction of high voltage bushings, effect of different faults on bushings, CNDF test results, different test methods for bushings diagnostic, and then we will continue with interpreting bushing CNDF values, some case studies. Then finally, we will have online demo test with Kapton 12, our product for capacitance and dissipation factor testing. And finally, we will cover Q&A session. If you have questions, you can write in chat box. Our team will manage it. And finally, we will answer all of them. At WiseGrid Energy, we have some products, especially for diagnosing power system equipment, also for motor condition monitoring. Alina T1 is multifunction substation test system. This device performs all electrical tests for substation equipment. So, for example, power transformer tests, CT, CVTs, or circuit breaker tests. Second one is Kapton 12. It's a 12 kV time delta and capacitance test system. It's a standalone test kit. And finally, MCM1 is a motor condition monitoring device based on current and vibration signature. Also, you can check our website, wisegridenergy.com. Feel free to contact us. And if you have any questions regarding our products, our projects, feel free to share it with us. At first, I'd like to invite you for watching our first webinar. It was about the basic of time delta measurements, some interesting points like negative time delta, some case studies, also different test modes in time delta. So you can watch it now in our YouTube channel, Wise Grid Energy YouTube channel. It's really an interesting webinar for starting tan delta testing. Why we measure tan delta and capacitance? It evaluates the condition of the transformer and bushing insulation, problems like aging and insulation decomposition or moisture ingress increases the dielectric loss, and that generates additional heat within the insulation. This extent of the energy loss is measured by dissipation factor. There are another important point which always is behind our minds, and we never check our test results. It's capacitance measurement. For power transformer, the capacitance value shows us the displacement or deformation of the windings. I will share some interesting case studies regarding this point with you. And for high voltage bushings, it identifies short circuits between the capacitive layers, which is really important for high voltage bushings. To measure dissipation factor and the capacitance of a power transformer, we need to do some steps. Firstly, the transformer should be de-energized and isolated from the grid, because if our transformer is connected to the current transformer or circuit breaker, the short length of the conductor will cause parasitic capacitor to the ground, and we will have wrong value for dissipation factor, especially when we want to measure CH or CL of the transformer, which is a capacitance from winding to ground. Also, the winding is connected to the bushing. So if our bushing is connected, for example, to a current transformer with the 5 or 10 meters conductor, so we will have parasitic capacitance in circuit. So please isolate the transformer completely. Then ensure the transformer tank is properly grounded, especially in commissioning period. Our transformer is in substation, and we need to make sure that the transformer tank is connected properly to the substation ground grid. And finally, connect all terminals of the same winding together. As you can see here in the picture, all 3 winding bushings are connected together separately and short-circuited, including the neutral point. Sometimes the guys forget to isolate the neutral point from the ground, and we will get a wrong value in this case, or the test kit will give an error for us. So we need to also remove the neutral from the ground and short circuit it to the other bushings. So for 2 winding transformers, we have 3 main target capacitances. It's called CHL, which is a capacitance between high voltage and low voltage winding. CHG is the capacitance between high voltage winding as the ground and the grounding tank of the transformer. And finally, CLG, which is the capacitance between low voltage winding and the magnetic core of the transformer, which is grounded. These 3 capacitances. But we measure other 3 capacitances. For example, number 3 is sum of these 2 capacitances. For number 5, we measure CLH again. It should be the same value with the CHL. Why we measure these 3 other points? Because we need to double check our previous measurements. If we just measure CHL, CHG, and CLG, okay, we are not sure that our previous measurements are good. Are they satisfying the transformer insulation condition or not? So we need to double check our measurements, and we do such measurements. In Kaplan 12 software, we have a dynamic wiring for power transformer dissipation factor testing. For example, if we want to measure CLG, so the software shows us connect the 12 kV output to LV, then input A to HV, and the measurement mode is automatically selected by the software. So if I change it to CHL, for example, or CLH, the wiring automatically and dynamically updated in the software. For the 3 winding transformers, we have 6 target capacitances which are important for us: CHL, CHT, CHG, and CLT, CLG, and finally CTG. But other modes we are measuring for also double checking our previous measurements. Also in Kaplan 12 software, we show all wiring diagrams that are related to the target capacitances. So the operator can just check the wiring, do it, and start the test. Also the test mode, for example, USD-A, USDB or GSTG modes are automatically selected by the software. Here you see some wiring diagrams relating to the three-winding transformer. For example, here we want to measure CHT, so the software shows us to connect 12 kV output to HV side, input B to tertiary winding, and the input A to low voltage winding. Then the USDB mode automatically selected by the software. Also, you can say it for other wirings and other target capacitance. For shunt reactor, we have just one test mode, high voltage winding to the grounded tank of the reactor. It's measured in GST mode. We need to short circuit all bushings together, then apply voltage from high voltage winding. Then we can measure the capacitance and dissipation factor of the HG capacitance. There is an interesting point regarding three-winding transformers. Here we've measured the three-winding transformer capacitance and dissipation factor. The rated voltage were 230 kV, 66 and 20 kV for this three-winding 160 MVA transformer. So here these are the target capacitances which was measured. CHL 9.64 nanofarad, and the dissipation factor CHT, CHG, some of these measurements, and finally CLT. Normally we look at the dissipation factor test results, and okay, you see all of them are okay and in good range. But if we look at the capacitance value, we see that for CLT, we've measured very low value of capacitance, 144.4 picofarad, but the other values are in range of several nanofarad. So what's the problem with this point? For a three-winding transformer, suppose that we have an arrangement like this. We have magnetic core, LV winding, high voltage winding, then tertiary winding. So when we want to measure capacitance between LV and TV, our HV is connected to one of the inputs of the device, and it will be guarded from internal side of the tan delta test strip. When we guard HV winding, so the capacitance between LV and TV will be very low, and we call it stray capacitance or parasite or capacitance in the circuit, maybe between bushings of the transformer or something like that. And this low value of capacitance, sometimes we get very high dissipation factor. Here it was in a good range, but sometimes it's in a range of several, maybe 1 or 2%, or sometimes we get negative value. In this case, in case of three-winding transformer, please don't think about this capacitance, and you can interpret this condition of the transformer just by measuring the other capacitances and other test modes. So in a three-winding transformer, one of the capacitances will be measured very low with high or normal dissipation factor, so we can remove it from our final assessment. Is it possible to find out what's the winding arrangement inside of the transformer before we start a tan delta test? I would say yes. If we look at the power transformer nameplate, we will see the impedance voltage or short circuit impedance for different arrangement of the windings at different tap positions. For example, here we have for HV to LV 16.15%. At tap number 1, for HV to TV, we have 25.84%, and finally for LV to TV, we have 56.72%. It means that our LV and tertiary windings are far away from each other. So our arrangement will be like this. And if I measure capacitance between LV and tertiary winding, the value of the capacitance will be really low. So it's not necessary to evaluate this capacitance in our final assessment. But please take care. Take a look at the reference power which these short circuit impedances are per unit. Usually it's based on high voltage winding power. For example, here 160 MVA, but sometimes manufacturer use tertiary winding power for per unit. So in such cases, we will have also higher value for tertiary winding short circuit impedance. But normally they use high voltage winding power. So we would say which winding have a higher short circuit impedance in per unit. They are far away from each other, and we will have low value of capacitance in this case. About the temperature correction, as you know, the dissipation factor is dependent on temperature of the insulation, especially for power transformers. In old version of IEEE standard, I mean IEEE C57.12.90, we had some correction factors for power transformer, but in newer version of the standard, it was removed because they said that the manufacturer are using different insulation inside of the transformer, different paper, different oil, so we cannot have the same correction factor for all type of the power transformers. So we need to get the correction factor from manufacturer of the transformers. But nowadays, the old version of correcting factors are used also in test kits. There are values like this table as you see here. But for newer transformers, it's recommended to get correction factor from manufacturer of the transformer. So about the assessment of the results, in IEEE C57.152, we have some limits for dissipation factor at 20 Celsius and 50 or 60 Hertz. For power transformer with voltage level lower than 230 kV, the maximum DF for new one is 0.5%. For higher voltage, it's in range of 0.4. But for natural ester and also for old power transformer, the dissipation factor can be up to 1%. But it's not hard restriction. I mean, I've seen a lot of transformers in the market are working with dissipation factor in the range of 1 to 1.2 or 1.3%. But the other interesting and important point is related to the capacitance. If the capacitance changes lower than 5%, it's acceptable. Between 5 to 10%, we should investigate the problems. At first step, we need reduce our test time intervals. And if it changes more than 10%, it's really critical. And we should not energize the transformer. We should find the problem and solve it. So please always firstly check the value of capacitance, then go to the dissipation factor, because if we have winding displacement or deformation inside of the transformer, the value of capacitance will change, but for dissipation factor, maybe it doesn't change because for paper degradation, also decomposition, we need some time. Finally, for assessment, rate of change of time delta is really important in comparison to the absolute values which we've seen in previous slide. The analysis is performed by comparing test results from periodic tests over the time, comparing with similar assets, and evaluating the trend, I mean rate of change. Also, complementary tests like DGA and oil quality tests are really important to assess the insulation quality. And we need sometimes to shorten our testing intervals to find out the problem inside of the transformer. Let's go for case studies. The first one is related to the magnetic core grounding. As you know, normally we ground magnetic core of the transformer from one point. Sometimes it's came out of the transformer. We have a point, it's called M point or something like that. And we can remove the grounding point and measure insulation resistance of the magnetic core to the ground. So in all of the transformers, the core should be grounded from one point. But sometimes the ground connection point got problem. For example, in this case, we had low energy discharge with DGA, and finally we decided to measure capacitance and dissipation factor. As you can see here, for a normal transformer, we have three capacitances: HV winding to the grounded tank, capacitance between HV and LV winding, and finally LV winding to the magnetic core of the transformer, which should be grounded. So we call it CL. But if this grounding connection is removed during the operation of the transformer, so we will have another capacitance in the circuit. We call it C core. At first, we will have a lower value for LV winding to ground capacitance because C core is added in series. The other point is related to the dissipation factor. In this case, we have measured dissipation factor at different frequencies, and we found that with increasing the frequency, the dissipation factor change very high. So in comparison with DGA results, we found that there is a problem inside of the transformer, and after internal check, we found that the grounding point of the magnetic core was removed during the operation of the transformer. Case number 2 is related to the high moisture level. Transformer T1 and T2 are in the same operation. They are parallel during operation. But as you can see here, if we compare the dissipation factors for both transformers, we found that for T1, it's approximately 2 times of the T2. And this was the problem inside of the transformer. Moisture ingress has occurred, and permanently through the LV bushings. So rust formation is visible, as you can see here in these pictures. And this transformer was located near to the power plant's steam towers, and it's exposed to the humidity. So if moisture enters inside of the oil of the transformer, as you can see here, rust can develop internally as well. So you see rust here in these pictures. Third one, as interesting one, is related to the winding deformation. These are test results of a transformer. First one is after the operation of Buchholz and differential relay, transformer is de-energized, and we've measured capacitance and dissipation factor. And this one is related to the previous measurement. So at first, if we look at the dissipation factor, we will see nothing. It doesn't change. So the dissipation factor is good. But if we look at the capacitance value, we see that the change is higher than 20%, especially for HV winding to ground. It doesn't change so more, but for other capacitances, the rate of change is really high. And this was the problem inside of the transformer: winding deformation, winding displacement, and also short circuit inside of the transformer. At first, we found it by winding resistance measurement. Then we've done capacitance and tan delta measurement, and we found, okay, we have buckling and winding deformation inside of the transformer. So please always check C before tan delta, because it shows us a very important thing, and we can find out the problem inside of the equipment. So we continue with the high voltage bushings. We have 2 types of bushings: condenser type or capacitive graded bushings, which are OIP, RIP, RBP, and the new generation of bushings, which are called RIS and RIF bushings. And the non-condenser type bushings, or we call them solid bushings, which are composite, compound filled, and SF6 bushings, especially for GIS. In this webinar, we cover condenser type bushings. For non-condenser type bushings, there are just hot collar tests, which we talk about that. So in condenser type bushings, we have a capacitive grading inside of the bushings. I mean, we have some aluminum foil paper, and they are impregnated in the oil. So we will have a capacitance network like this. We have central conductor here, then aluminum foil, which we will have a capacitance like this. From center conductor to the last aluminum foil, we have C1. Last aluminum foil is connected to an electrode and came out of the bushings. We call it test tap. So test tap is normally grounded during operation of the bushing. And between test tap and grounded flange of the bushing, we have another capacitance. We call it C2. This is another picture which shows us the different components of the bushings. It's terminal, aluminum conservator, oil level integrator, porcelain insulator on air side of the bushings, aluminum flange, which we have test tab on this flange, some extension, flange extension for bushing CTs, epoxy resin side, and corner ring, which is inside of the transformer. We have different naming and different terminals in bushing. First one is test tab or measuring tab or tan delta tab. It's for IC-based bushings. In test tab, the last aluminum foil is connected to a terminal and it's out of the bushings. We normally ground it during operation. So test tab is here. We have C2 and test tab. And it's typically C2 is in range of 500, 600 picofarad. Also, the test tab voltage is up to 500 volt. But for potential tab or voltage tab or capacitance tab, the potential tab is the capacitance between last layer and one layer before the last one. I mean here, the potential tab is here. So if we have a potential tab in high voltage bushing, its capacitance range is in range of some nanofarad, 1 to 5 nanofarad. Also, we can test it with higher voltage range, maybe 2 or 3 up to 5 kV. It's normally okay for potential tab. It's especially for IEEE and C-type bushings. Both terminals should be grounded during the normal operation. Also, we can use them for bushing monitoring. But there is a question here. Can we test from test tab while the potential tab is grounded? Normally, when a bushing have two potential and also test tab together, both tabs are grounded by the cap. So when we ground the potential tab from here, we normally open the test tab electrode and we want to measure. But when the potential tab is grounded, from here, suppose that we forgot to open the cap and we apply the voltage from here and we want to measure from tab. So when we have a grounding connection from potential tab, okay, from test tab, we will not get any value and maybe test kit will give us some error. So if a bushing has both potential and test tab, we need to open both of them and measure bushing capacitance and dissipation factor. The another point is related to the values. When we measure C2 of the bushings, when the bushing has a test tab, maybe it's 500 picofarad. But when we install bushing on a transformer, this 500 picofarad value changed to maybe 600 or 700 picofarad. It's because of the stray capacitance inside of the transformer. So in test tab, we will have other values for C2 when the bushing is installed in the transformer. But for potential tab, the value never changes. When we have 1 or 2 nanofarad for potential tab of the spare bushing, and when we install it on a transformer, we will have the same value for potential tab because stray capacitances doesn't influence for potential tab. This is one major difference between these two tabs. There are different type of test tabs in the market. All manufacturers use a different type of test tabs, also different type of caps. For grounding the test tab, we should be aware of them, and when we want to measure dissipation factor and tan delta of the bushings, so we need to open test tab and connect our test kit to this point. So if the bushing has both of them, like this one, the smaller one is test tab and the larger one is potential tab. Okay, what will happen if we leave the test tab open? Assume that we have a bushing, C1 is 250 picofarad, C2 is 650 picofarad, and the rated voltage of the grid is 220 kV. If we leave the tab open and we energize the bushing, we will have 61.1 kV on test tab. So test tab cannot withstand this voltage. We will have electric arc, and the inner capacitive layer of the bushing lost their reference to the ground. We will have a floating potential, which leading to a partial discharge, overheating, and finally bushing failure. So please always make sure that after your test tab is grounded properly, or if we did it open, or we have some loose connections during closing cap of the test tab, we will have some cases like this, and in a long time maybe it will damage our bushings. There are other two terminals in instrumentation transformers. I just want to review it here. First one is F terminal. F terminal is related to current transformers. It's similar to test tab. If there is an F terminal in a current transformer, we can measure C1 and the C2. And L terminal or NHF is related to capacitor voltage transformers. End of the C2 here, which is always grounded or connected to the PLC, I mean power line carrier. So why we measure capacitance in high voltage bushing? Because it shows us partial breakdowns inside of the layer bushings, incoming of the oil into the cracks of solid insulation, especially for RIP, RIS, or RIF bushings. Oil level decrement is, we can find it easily by hot collar test. Also, if our test tab has open loop or it's grounded from inside of the bushing, we can easily find it by capacitance measurement. Regarding dissipation factor, it shows us aging and decomposition of the insulation, water content, any bad contactor inside of the bushings, and any cracks or partial discharge or insulation degradation related to paper and oil of the bushing. There are some faults which affect the value of C and DF. In a normal operation and normal condition, the value of capacitance and tan delta should be constant. I've seen a lot of cases which the value of tan delta maybe is in range of 0.35% for 10 years. But when we have a problem inside of the bushings, these values will change. For example, if we have interturn short circuit, the value of capacitance will increase because our series number of capacitances will decrease, so our total capacitance will increase. Tan delta maybe will be constant because interturn short circuits occur when we have high voltage switching inside of the power grid, and then these switching over voltage damage our bushings. For moisture ingress, the capacitance value, also tan delta value, will increase. For contamination, capacitance value depends on the type of contamination, but the tan delta value will increase. And finally, for oil leakage, the value of capacitance will decrease because instead of oil, gas comes into the bushings, and the permittivity of the gas is lower than the oil, so total capacitance of the bushing will decrease. But for dissipation factor, it decreases at low voltage, but if we increase test voltage up to 10 or 12 kV, because of the partial discharge inside of the bushing, we will get higher value for dissipation factor. We have different test methods for high voltage bushings. Normally, we just measure C1 in USD mode, but there are other test methods which help us to find out the problem. They are diagnostic test methods, so normally we don't need them. Normally, we just do USD test mode for C1. Let's see what are these test methods. Before starting the test, we need to de-energize and isolate the transformer. We should be sure that transformer tank and bushing flanges are properly grounded, and we should connect all terminals of the same winding together, including the neutral point. I've seen that guys, they say, okay, if you want to measure tan delta of the bushings when it is installed in a transformer, it's not required to short circuit it to other bushings. Here I have a case. This bushing, it's a new bushings, and before installation we measured the dissipation factor. It was in range of 0.25%, but after installation, without connecting it to the other bushings, we have measured the 0.617%. It's nearly 2.5 times of the dissipation factor. So it shows us that if we want to measure a single bushing on top of the transformer, we need to short circuit it to other bushings. And the other point is we should ground all unused windings to prevent any induced voltage during testing. I will explain about this point in next slide. It's for safety side. So first test method is called overall test of the spare bushing. When we have a spare bushing and before installation, we can test it in overall mode. Just we need to apply voltage from center conductor, then connect test equipment to the bushing flange and measure in GST mode. The other test method is main insulation test, I mean C1 of the spare bushing. We apply voltage from center conductor, connect input A or input B of test device to the test tab, and we measure in USD A or B mode just C1 of the bushing. What's hot collar test? Here I have two cases. One bushing is filled with oil. It's full of oil. The other one, we have oil leakage inside of the bushing. So when we have a collar here and we apply 10 kV and measure from center conductor, okay, I have oil inside of the bushing, and the value of capacitance and dissipation factor is in normal range. But when I have oil leakage inside of the bushing and I have a collar here, when I apply 10 kV, I will get a higher value for dissipation factor. Especially at hot collar test, we measure active power, and the active power should be lower than 0.1 watt. I will explain it in next slide. So the hot collar test help us to find out all leakage inside of the bushing. Typically also we can use it for bushings without a test tab. It doesn't stress the insulation as much as C1 test. Also, it's less sensitive to insulation failures than C1. It's useful for verifying oil level in bushings without sight glass or oil level indicator. Also, if our bushing oil is lower than the oil level indicator, we can check its level by hot collar test. Also, the test voltage is typically 10 kV. It's focused on insulation only near the collar area, so we can move the collar at different position along the bushing to assess different sections of the insulation. Regarding acceptance criteria, the watt loss should be lower than 0.1 watt. It's acceptable. It's a rule of thumb, but there is no standard IC or IEEE standard for this value. Also, we can compare the measurements with the sister unit, I mean with other phases or with similar transformer. And we typically don't assess the tan delta value when we perform hot collar test. We just look at the active power, and it should be lower than this value. About the test up insulation, for a spare bushing, we apply voltage from test up, and then we connect input of the device to center conductor. We measure in GST-GA mode, which gives us the C2 value, but always check the voltage of test up. It's normally 500 volt. Because if we apply higher voltage, we will damage the test tab. And if test tab have a bushing that is damaged during operation or during test, there is no chance to repair the bushing, and we should remove it and we replace it with new one. So always be careful about the test tab. If a bushing is mounted in a transformer, so for C1 testing, we need to short circuit all bushings together like this. Then connect input of the device to bushings test tab, then measure in USD-A mode. We need to repeat it for all bushings. But important point is that we need to connect other unused windings to ground. Why? When we apply voltage from HV side of the transformer, here we have 10 kV. So this 10 kV comes to the CHL. Then with CHL and CL, we will have an induced voltage here. Maybe I apply 10 kV from here, and I will get 5 kV or higher voltage here. So if the operator touches LV bushings, he will get an electric shock, and it's in some cases it's really dangerous. So always be careful when we test HV bushings. Our guys think that okay, there is no risk at LV side and I can touch LV bushings, but here, as you see, because of this capacitive coupling, we will have induced voltage here, and in some cases it can be really dangerous. So always ground unused winding. So in this case, it's okay, and there is no risk. There is no risk for test operators. And for testing C2 after installed bushings, as I said before, the value of C2 after installation will be different for the bushing which is not installed, so we cannot compare it with the bushing nameplate, but it's just for diagnostic test. Especially when the bushing flange ground connection has problem, we measure higher value of dissipation factor for C1. And in such cases, we need to measure C2 to find out what's the problem. Or our test tab connection sometimes has problem, and in such cases, we need to apply voltage from test tab, measure C1 and C2 again, and double check our previous measurements. Regarding negative DF, we've talked more in our first webinar, so please review our first webinar, but there are some points, especially for bushings, like high surface leachage currents, external interferences, unshorted windings, and grounded bushing tabs. Sometimes bushings tabs remain grounded when we open the cap. We need to remove some cover and connect our test kit leads. So in such cases, make sure that all cover is disconnected and we are measuring C1 at a proper way. For assessment, firstly, let's check values for capacitance, because it's really important for high voltage bushings. The rate of change, if it's lower than 5%, it's acceptable. Between 5 and 10%, we should investigate the problem, and if the value of capacitance change higher than 10%, it's critical. These are for C1. For C2, we don't have any special absolute limiting standards, IC or IEEE standards. We should check the manufacturer recommendation for C2. For dissipation factor assessment, manufacturer says that if the dissipation factor is written in nameplate of the bushing, for newer bushing, according to IC 60137, it should be written in the nameplate, so we can check the measurement values with their nameplate value. We call it DF, reference DF. So if measurement is up to 2 times of the reference value, it's in acceptable range. Between 2 and 3 times, we should investigate the problems. And if the measured value is higher than 3 times of the reference value, it's really critical. But if we want to compare with absolute values here, these tables are from IEEE and IC standards. For example, for OIP bushings in IC standard, the maximum value is 0.7%. In IEEE, we have it 0.5%. But please take care that these values are for old bushings. I mean, more than 15 or 20 years old. So if I have a bushing which is installed maybe 2 or 3 months ago, 6 months ago, 1 year ago, and we get this value in less than 15 years. So it shows us that the bushing degrades fastly and quickly. So we need to check the condition of the bushing. Also, there are some limits for dissipation factor of C1 at 20 Celsius at Sigrid White. Here it's interesting because they tell about frequency at 15 hertz and 400 hertz. We see that for new OIP bushing, the tan delta doesn't change more. Also, for old one, the rate of change is really low. I will explain about this frequency variation or frequency sweep more in next slides. Regarding temperature correction factor of the bushings, it's similar to the power transformer. There is no standard which tell us unique values for all type of bushings, but there are temperature correction factors which are used in test kits which are in the market, like this table. But please take care that these temperature correction factors are for bushings normally with 0.5% of moisture. What does it mean? Here you see a tan delta variation with temperature for an OIP bushing at different level of moisture. This curve comes from ABB. So if we take a look at this one, we see, okay, if we want to correct tan delta from maybe 60 Celsius to 20, the correction factor depends on the bushing's moisture level. For higher one, we need higher temperature correction factor, but for bushing with moisture lower than 0.5%, maybe we never need correction factor. Here, ABB has some interesting idea. They say that measure dissipation factor of the bushing at higher temperature, maybe instantly after de-energizing the transformer. The temperature is 60 or 65 degrees, so measure at first dissipation factor of the bushing. Then repeat your normal electrical test or other test. Then after 2 or 3 hours, measure dissipation factor again, maybe at 30 or 25 degrees. If dissipation factor changes more between these two temperatures, it shows us that the bushing has problem inside. So it's really interesting for checking and conditioning the bushing insulation. But the other point is frequency sweep. Here I have a case for a transformer, 2 bushings, 2 HV and LV bushings. You see the results here. First measurement at 17 Celsius, the other one at 45, instantly after de-energizing the transformer. As you can see here, for low voltage winding or secondary side, we see the dissipation factor doesn't change more by temperature. Here at 45 degree and at 24, at 17, we see the dissipation factor values are in the same range. Really, they are equivalent. But for high voltage side, we see that, okay, at 45 degree, we have a dissipation factor 2 times of the 17. So it's not accepted, and we should look for insulation degradation or something like this. Also, in that case, we've done VGA analysis, and we found that low energy discharge or partial discharge, we have it inside of the bushings because of high moisture or cavity. And finally, the frequency sweep showed it to us. So instead of increasing the bushing temperature, which is an interesting way to find out the problem, let me plot it again here. We have dF, Vs temperature. In an aged bushing, it's like this. When we increase the temperature, the dissipation factor increases with higher rate. But instead of increasing the temperature, we can decrease the test frequency. So they are same. You can decrease test frequency or test dissipation factor of the bushing at high temperature. And because of that, at Kapton 12, we've decreased the output frequency to 1 hertz. We can test from 1 to 500 hertz. Other cases related to the bad contact in HV terminals of the bushings. So when we have a bad contact in HV terminals, we get higher value of dissipation factor. After repairing and removing it, we will get lower value for dissipation factor. In this case, we can repair the bushing. It's not necessary to remove it and replace it with new one. Just we need to open the HV terminal, solve problem, and put a new one. Or other case, which is similar to the previous one, when we have a thermal fault in HV terminal of the bushing, we can easily repair it and get lower value for dissipation factor. Other cases related to the high value of DF, these two transformers are in parallel, but the dissipation factor for one of transformer bushings are really high for all three phases. And this was the problem, internal short circuit, gas generation, and problem like that. The other test is voltage sweep. It means that we change voltage from maybe 500 or 2 kV up to 12 kV. It helps us to find out any contamination problem in outside or inside of the bushing. So when the dissipation factor changes by changing the applied voltage, also it's called the tip-up test. It's originally for rotating machines, but we can use it for bushing and transformer testing. So when dissipation factor changes by changing the voltage, it shows us there is problem in our connections or bushing connections or inside of the bushing. Other cases related to the test tab. When we see test tab from outside of the bushing, okay, we see it's really a good terminal and we can make our connection in easy way to that. But please take care that inside of the bushing, this test tab is connected to an aluminum foil. And if we don't take care about this point, we can damage it easily. And if we damage the test tab of the bushing and disconnect it from the aluminum foil, there is no way. We should replace the bushing and we cannot repair it. Here you see for two bushings of a power transformer, we've measured C1 and C2. For phase 1, you see C1 and C2 values, also dissipation factor are in normal range. But for second phase, as you can see here, the dissipation factor value also is in normal range. But if we look at the capacitance value, we will see that, okay, there is a problem inside of the bushing. And because of this low value at C1, we repeated C2 measurement and we found that, okay, if we apply voltage from test tab, also we don't get a proper value. And in this case, we've replaced the bushing with new one because test tab was disconnected from inside of the bushing. And the final point is related to the flange grounding. Always manufacturer, for example, here you see from ABB technical guide, they say that you should ground the flange connection of the bushing for safety and for increasing the life of the bushing. But here I have a case. A bushing was, the dissipation factor of the bushing was measured at 2022 and 2024. But for one phase, we have measured higher dissipation factor at routine test. And finally, we've checked the bushing and we found that, okay, there is no flange grounding. They forgot to install flange grounding because there was a problem inside of the transformer. They removed the bushing and installed it again, but they forgot to install flange grounding. And because of that, they got higher value for dissipation factor. So always check flange grounding at first when you have higher value for dissipation factor, test connections, test device, then go deeper and do other tests. This is Kaplan 12, our standalone test kit for capacitance and dissipation factor measurement. The maximum voltage is up to 12 kV, output current up to 300 milliamp, frequency range between 1 to 500 hertz. Also, it's designed in modular, so all parts of the device like touchscreen, LCD, or inverter measurement and power supply modules can be removed easily from the device. Also, the accessories and wirings are really simple. You just have a single device and you can start and do your test easily. So let's have an online demo test with Kaplan 12. Then we will go for a Q&A session. I have a Kaplan here. I want to connect it via Wi-Fi. So let's share my screen. Okay, this is Kaplan software. If we want to define a project, we can start from workspace, define our location, our equipment in location, define some tests for our equipment. For example, I want to measure time delta of transformer, bushing, or frequency sweep, tip-up. We can define and manage all tests here. Also, there is an online software. We can define all projects there and import it in the device. Then go beside the transformer, just click and start the test. For example, here you see different test modes for frequency sweep, or for maybe for voltage, tip-up, or single. Also, another interesting point is for wiring. For example, if I select CHL here and I go to the wiring, the device, the software shows us the correct wiring. If I change it maybe for CLG, wiring will be changed, and as you can see it here, there is a menu which shows different parameters of the device, temperatures, input, output voltage, or something like this. Let's just start a quick test to see the device speed. For example, here I have a test setup, just start. I'm in a laboratory, so everything is safe. So I will start the test in USB-A mode. And as you can see here, the voltage go up, the device measures values, and I can also change these to other parameters which I need. And it stops the test. I have the value here. Also, you can use different test methods like frequency sweep or tip-up tests. Okay, let's go back to our presentation. Okay, thank you so much for attending this webinar. Please check our website. We have some articles, case studies. Feel free to keep in touch with us with info@wisegridenergy.com. If you have any questions, I'm here. Please feel free to ask. Okay. Mr. Luis, nice to meet you. Okay, you have a bushing with dissipation factor at 60 hertz is about 0.8%, and when they increase the frequency up to 400 hertz, they get 0.53. They get, 2.42%. It means that by increasing the frequency, the dissipation factor increases. Also, when they reduce the test frequency to 15 hertz, they get lower value for dissipation factor, 0.53. And they repeated the tip-up test 1% at 2 kV and 0.8% at 10 kV. So please let me know about the capacitance value. Also, it changes with frequency and voltage or not. Because if the capacitance value doesn't change with this frequency and voltage variation, it means that there is a loose connection or bad contact in your circuit. Okay, thank you. Capacitance didn't change with sweep. Okay, these cases show us that there is a loose connection in your bushing terminals. Especially, please check test tab because when you increase the voltage and the dissipation factor value decreases, it means that by increasing the test current or increasing the frequency, the problem is the condition of the problem change. So it always related to the bad contacts in bushings or your test terminals. So is there any question? Please feel free to ask. You're welcome, Mr. Luis.
Great presentation here. You know, I enjoyed it too. What I think one question from my side, you know, like, because it's interesting to see all these sweep that we talk, voltage sweep and frequency sweep. So if I'm just, you know, curious if you have option to do, let's say we're diagnostics, we have a problem with a transformer or a bushing. If you have only the option to do the frequency sweep or voltage sweep, like if you want to pick one, which one do you think is more important overall?
Thank you, Dr. Ali. It depends on the condition. I always use frequency sweep because all devices in the market have 10 or 12 kV output, but frequency sweep is really interesting, and it helps us to find out insulation problems. I have a lot of cases which we've diagnosed with frequency sweep, but by applying voltage up to 10 or 12 kV, we never found the problem.
The box that you presented, Captain 12, is the wider frequency range compared to commercially available. One number to start with. I was listening to another presentation yesterday that was from IEEE.
Dr. Ali, I don't have your voice clear. So maybe he has some problems, internet problems. Is it necessary to cooling the bushing before testing? Yes, I showed a case for voltage sweep. If the bushing outer side is dirty and it's not clean, so we will have wrong values also for C1 dissipation factor, because we have some stray currents from outer side of the bushing, and it affects our test results. So always please clean the bushing, then wait to be dry and do your test. No, there is no limit for C2 dissipation factor. I've seen an ABB document which they say that up to 5% for C2 dissipation factor is allowed. So about 2.3%, just check flange grounding. So, and you cannot compare it with the bushing nameplate, Mr. Lewis, because when we put a bushing on a transformer, the value of C2 will change, also the dissipation factor value. Okay, guys, thank you so much. Dr. Ali, if you have comments, please let us know, then we can end the webinar. Okay, thank you all guys for participating in this webinar. Wait for our next webinars.
Absolutely.
Thank you so much.
Thanks a lot, and we're looking forward to see you in the coming webinar. Thanks for joining us. Have a good one. Bye.